All right, so this week's lab is on Kirchhoff's rules. We touched on this a bit last week with the Ohm's Law lab, but it's just, you think of that lab as the warm-up to this week's lab. Uh, Before I go into the procedure for the lab, I'll say that our second quiz is now available on Canvas. Um, since we're going to be covering, a bit harder material with each passing lab, you can expect the quizzes to be a bit more difficult going forward. So make sure you're ready. Make sure you have a calculator ready, some scratch paper. Um, yeah, if I make a quiz that's a bit more difficult, I'll always try to reduce the number of questions too. I'll make it manageable so you can finish it within 20 minutes. Okay, let me go over this week's lab. Okay, so on Canvas, we have um, the assignment page. This one is more difficult. They're just sort of increasing in difficulty. This one is worth a lot. It's worth 80 points. It's the most of all of the labs so far. Going into the instructions, I don't see if you could access these right now, and let me know if you could pull those up because I was having trouble with this in another lab. But if you can open these, you will see the instructions that look like this. Same as always, make sure you include your own introduction somewhere near the top. There's some background material if you wanted to review, and maybe my notes aren't out right away. And we have this lab. It's going to be the exact same. We have a simulation right here, and it's going to be the exact same program as last week. Let me go to it, except instead of hitting intro, we're going to click on lab right here. And in here, in the lab section, it's pretty much the same exact thing, except they give us a couple more tools over here on the right. And eventually we're going to be using some mystery resistors down here at the bottom. Ultimately, it's going to be the same thing, arranging circuits and measuring the voltages and measuring the current through various parts. Okay, it will start out simple, measuring a small series circuit. We're gonna, this time we have this switch we're gonna include. And from there, oh, that's something I could clarify. Make sure to always have your uh, probes for the voltage in the correct orientation. What do I mean by this? Let me put that away. So we're just looking at voltage with these two probes right here. And let me make a small circuit. Now this is not a circuit that is in the lab. This is just for my example. Let me have a circuit with a battery, a light bulb, and a single resistor. Okay. Now, when we measure with these probes, the red and the black, you can think of them as positive or negative. It doesn't matter specifically as long as you keep the orientation the same. You will get the same, or you'll get consistent signs for your measurements. There we go. a thing to do. Remember, for measuring voltage, we measure across something. So let's put the black one on the bottom side of the battery and the red one on the top. And we can see it's a positive 9 volts. Okay, what do I mean by a consistent arrangement? So I'm going to imagine I have those probes and they're sort of fixed in that position. The red one is in front of the black one. So I move this along and I move it to the back side of, or the farthest side of this light bulb. And I put the black one on the closest side of the light bulb. So closest to the battery, the path of the battery. You can see now it's a negative 9 volt, negative 4.5 volts. And we can mark this negative value as consistent and correct. Okay, moving these probes again, being consistent. You're going to move this red one to the farthest of the circuit element, and then the black one will move to the closest to that. It says the copper top side of the battery. You can see this is also negative 4.5 volts. And we don't have to go all the way back to the battery because we know this will go all the way back to the top, bottom, positive. Okay. So there are written instructions on this, making sure that you are arranging this properly. Where were they? They were right. It's right here. So make sure you just keep your the probes consistent, and you can actually take the values that are written on the meter. Okay, so we have this simple arrangement and do some measurements. We're going to get a bit more complex arrangement, and we're going to take measurements. And a bit more complex. And I think mostly we're measuring today. I don't think this is something we're calculating. Actually, we are going to calculate a little bit with this circuit. So just remembering how to add resistors in series and parallel will help with this. Okay, the measurements for this bit go in the table. So just filling out the table, you don't have to do this little bit as long as the table's filled out. Okay, and at the very end, we have this new thing that this is called a galvanometer, I believe. Where is it? Galvanometer, right there. Okay, and it uses a process of differing voltages on different sides. And this uses both Kirchhoff's rules at the same time. And we're just basically finding a mystery resistor for this arrangement. But it does, walk you through pretty generously, like normal. At the very end, that's what we're gonna find our mystery resistor. And at the very end, that's where you fill in your own conclusion. There's no spot that's written that says you have to do it, but you always have to include one. You always have to include a introduction. And you fill out this survey on how long the lab took and how were the instructions written. Okay. Again, these Google Forms, this survey that's not graded, it's anonymous. So you just fill that out with your opinion on the instructions. Okay, are there any questions about um, these instructions or procedure? I will say that since it is, largely uh, the same process, the same material, or should say the same types of experiments as last week, I'm going to say after my notes that I'm going to go over in a bit, or up next, after my notes, I'm going to say the people who want to go, they can leave. The people who want to stay and work on it, I'm going to be here and I'll help you out. I would suggest everyone work on it because you can tell it's going to get a bit tricky near the end. Okay. So if you have questions, shout them out. I'm going to switch to the notes. Okay. All right. Kirchhoff's rules. So I brought these up a bit last week, and you saw them at the very end of last week's lab. They are important enough that we have dedicated a whole lab to them. What are they? Well, there are two. They're not specifically numbered. They're just given sort of their names. There is the voltage rule. Commonly just said voltage rule, or it might be referred to as the loop rule. And there is the current rule. Commonly just referred to the junction rule. Okay, let's put some definitions for these down, and I'll refer back to them uh, at a later time. So the voltage rule, what that states is the sum of all the voltages within a closed loop is 0. And I need to specify it's within any closed loop. Let me write this down. So the sum of voltages within any and this is within a circuit. That's what I'm referring to. Within any closed loop uh, in a circuit is 0. And I want to specify, or maybe I'll just underline, any closed loop. Okay, I will show this in a bit. The junction rule, or the current rule. This says that the current that flows into a junction, or you think the total current flowing into the junction is the same as the total current that flows out of the junction. So I could just phrase like that. Total current. Instead of flow, maybe I'll just say enters. The total current that enters is the same as the total current that exits the junction. All right. So we have our Kirchhoff's rules. Let me make a little diagram to demonstrate these. And let me go like that. So if you're following along, down here, I'm just going to do kind of the same thing we saw last week, or I put in my notes last week. A battery, positive side right here, and one resistor and let's say two resistors, like that. R1, R2. I will just call the battery V, capital V. Right, so what we did, this is similar to the experiment last week with the two light bulbs. You can commonly just think of light bulbs as resistors. You know, there's a bit of metal that has a lot of resistance in it, and the metal heats up significantly enough that it glows, and that's a light bulb. It's just a fancy resistor. So this is similar to our light bulb experiment last week. In that case, we had a battery that gave out 9 volts, and each of these light bulbs, or each of these resistors in this case, we measured the voltage across them was 4.5. This is let me put this over here, or I'll put it up here. This was assuming that they are the same, so R1 and R2 are the same resistances. And this is the voltage going across each one. Okay, let's draw what kind of loops we have. This is just one big loop like this. What can we see that's connected in this loop? That's what we can analyze. So within this loop, so we have one battery and two resistors. And the two resistors are the same resistances. So they need to split up the total voltage equally. Let me go like this. So it was a bit more interesting, or a bit more apparent, looking at in one case when a resistor was different, or when we had a parallel circuit. Let me do that parallel example from last week. That's okay, and the junctions right here, I'm just going to make those dots so I see them and I notice them as junctions. And in fact, let me move all of this down a bit over here. Okay. So in this case, similar to the, experiment, we had the battery that was supplying 9 volts. So the battery is pumping out 9 volts. You can think of this with the series or also the parallel case. Oh, no, that's what I forgot to do. So let me write the equation for the voltage down here. So for this series example, I knew I was missing something. For this series example, I'm going to call the voltage supplied by the battery, that 9 volts, I'm going to call that positive. Because in my mind, it makes sense to say the battery is supplying the voltage to the circuit. So it is supplying positive 9 volts. 9 volts, like this. And each of these resistors, R1 and R2, are consuming the voltage. So it takes voltage for the current to cross them. So in my mind, I just break that down into saying consuming. It makes sense for me to say those are negative 4.5 volts minus, and that's from R1, and another 4.5 from R2. And, that's how my mind can keep things consistent, while also, if I keep things consistent measuring with my measuring tools, it will also line up with this way of thinking, and we see the voltage does sum to 0 in that series example. Okay, so that was what I forgot on this. Now let me go over to this parallel example. We had a battery that supplied 9 volts. And what did we measure? What was the voltages across each of these resistors? R1 and R2. These were light bulbs last week in the experiment. But we saw that in one of them, it was 9 volts, and in another one, it was also 9 volts. How can that happen? Well, we need to look at where are the closed loops. Let me make this in different colors. So let's draw one loop that we see, sort of this small loop right here. Okay. So you could follow closely to, the path I could have drawn on the wire itself, but maybe I'll just do that. So, or that makes it better. I'll call this loop 1. What elements are in loop 1? There is one battery and there is one resistor. So let's write these equations out. So the battery is supplying a positive 9 volts, and that one resistor, even if I could either measure it and check, or I know the voltage rule, I don't technically have to measure because I know it has to be something to sum to 0. I can measure the voltage across this, and it was 9 volts. Okay, I need to get rid of that. There we go. Okay, 9 volts equals 0. Okay. Now, what was another thing we had to measure? We measured the voltage across R2. Why was that one also 9? Let me. Okay, I'm back. If that happens again and I don't come back, everyone is free to just, you know, stick around and I might, work it out, but I wouldn't keep you. Okay, where were we? I need to go back to this. Okay. All right. Okay. Why was this one also 9 volts? We had to consider this large outer loop. So the path that doesn't go through R1, it's this one right here.
We're looking at the Word document.
Oh no. What's going on? Okay, that should be good. Hopefully. All right, it's this outer loop, this large one that goes through and around, goes through R2 and comes all the way back like this. That is the large outer loop I'll call loop 2. What elements are in loop 2? There's one battery and there's one resistor. Same sort of thing as before. The battery is providing the voltage, so I'm going to call that positive. Positive from the battery. And this one resistor is free to take up all 9 volts. 9 volts. So that there is a sum of 0. Now, there is one final loop I have not talked about quite yet. Yellow. It's this third sort of in-between loop right here. Now let's make this loop, let's make it go like this. So it starts here, that resistor goes around like that. Actually, let me go, it doesn't quite matter where the arrow ends. I'm just making a loop. I'm going to call loop 3. All right. What's happening in loop 3? How can I analyze this loop when there's no battery in it? How can I conceptualize? Well, think of there is this, how can I put these values into the equation? Because since it is a loop, it does have to follow the loop rule, the voltage rule. What values do I assign? I don't know which one is positive or which one is negative. There's no battery that I could automatically assume is positive. So what I can do is go like this. Let me get rid of that just for a minute. I'll put it down here. Since loop 3, the direction that I've, chose for this is clockwise. I could have picked counterclockwise. It's up to me. But since I chose clockwise, it will go this way through R1. And it will go this way through R2. Now let's see how those directions line up with those other 2 loops. So for red, for that first loop, I also chose clockwise, and that meant it was going out and it was going this way through R1. And let's look at loop 2. Loop 2 was also going clockwise, and it was going that way through R2. So now I have this sort of consistent way of assigning a positive or negative sign. I could say that since um, these two arrows, these two paths of the loops I've chosen, since they are opposite, I'm just going to call that negative. I'm going to do yellow. I'm going to call that negative 9 volts. And since these two the paths align, I'm going to call that positive. Now, this is where, the conceptual understanding kind of breaks down, and it is just a matter of being consistent. I should have erased that. There we go. It doesn't necessarily mean that R2 over here is somehow providing voltage. This is just my own internal system of making sure values and signs are consistent. Okay, so that's something that's probably the most complex thing about if you were to calculate this. So let's go on to real quick. I should have put this before. This is the voltage rule. Current rule won't take up that much space. Current rule. Okay. So we have, I'm not going to do a whole circuit. We're just specifically looking at a junction. If your circuit diagram doesn't have these dots, you could fill in the dots yourself, just so you realize there's a junction there. The current rule focuses on the direction and amount of the current. So let's say the current is flowing in from this way. So into the junction, into the dots. I could have made this a large sort of dotted line like that, but I'm just going to call it a dot. So into the junction, recall that's the first current, I1. And let's say after this junction, we say that the current is flowing that way. We call that I2. And let's say it's going that way. Call that current 3. So this is simply just a small addition problem. If the current that is entering the junction is I don't know 10 amps, that's a huge amount. If 10 amps are entering the junction, then we should know that I2 plus I3, 2 plus 3, should sum up to be 10. So I1, I2 plus I3. So enters, exits. And this is, for any direction that the current is going. Let's do, one like this. Let's say the current is going that way. Call that the first one. Let's say we're going to keep the lettering the same, or the labeling the same. Let's say that one is also entering the junction. So I can't I can't make this one also enter the junction. There's nowhere for the current to flow. So that will be coming out of the junction like this. So the current into the junction is equal to the amount of current flowing out of the junction. 2 amps. This was, 5 amps. We expect down here to have 7 amps. And then I didn't finish this example. 10 amps entering. If we measure it over here, 6 amps, then without even needing to measure, we know that over here we have 4 amps. Okay. All right. Let me go like that. Are there any questions on the notes or the lab? Again, I don't have any sort of thing I'm checking off today. I'd encourage everyone to stick around and work on it and ask questions. I'll be here the whole time. Yeah, let me make the breakout rooms and all of that. Okay, there was a question. The current flow is opposite of the electrons in the, that are in the simulation. That is true. So that's actually, a good point. Let me, this is, I think it's interesting. So, so it doesn't matter what the circuit looks like that. So commonly we have positive and, we're just labeling the current is going this way. And this is just sort of the misunderstanding by, it was actually Benjamin Franklin when he saw that the positive current was flowing this way. And he labeled that, oh, the current, that's the direction. It's got to be going that way. Because positive current, the positive flow of charge is going that way. But the thing is, the positive charges, later on when we've done more tests and experiments, we've noticed that the positive charges, the protons, they do not flow. It's the electrons. Those are negative. So just by, convention, we're calling this positive flow of charge when actually what is happening is the electrons, the small electrons in here that are negative, are flowing the other way. So that's where that came from. And that's why it's reversed. You could blame Benjamin Franklin. Okay. Breakout rooms. It's just because, they didn't quite understand what electrons were at that time. But he had to label it something. Okay. And all right, the rooms are open. and I'll be here if you have questions.